So a very good evening to all of you present here in today's lecture of real analysis. So basically in this lecture I will start from so basically here we start from some illustrative examples and basically in this lecture I will discuss about uh, the uniform convergence, differentiability, integrability and many more things. So first of all, I will recall that what is the uniform convergence, what is the pointwise convergence. So basically, we discuss about the sequence and series of the function, which is very important concept of the real analysis. Basically, it is a very important concept of the real analysis. So here we start from the very important concept of the pointwise convergence. Okay. So first of all, we recall what is the pointwise convergence, what is the uniform convergence. After that, we go through the continuity and the differentiability of the functions. So basically, what is the point of the convergence? So pointwise convergence. One word. So what is the definition of this? Suppose that suppose that suppose that Fn is a sequence. Fn is a sequence of functions Fn such that A to R and F such that A to R. Okay. Suppose Fn is a sequence of function and Fn is a mapping from A to R and F is a mapping from A to R. Then Fn tending to F pointwise on A if Fnx tending to Fx as n tending to infinity for every x belongs to capital. So what is the pointwise convergence? Suppose that Fn is a sequence of function. We define two mapping Fn such that A to R and F such that A to R. Then Fn tending to F pointwise on A if Fnx tending to Fx as n tending to infinity for every x belongs to A. Okay. So first of all, we solve two examples. We solve the example. So example is that Fnx is equal to e to the power x by n and gnx is equal to x to the power n, so that f comma g both converges, both converge pointwise on close 0, 1, on close 0. So what is the solution of this? Solution of this. So here two sequence of the functions are given. Fnx is equal to e to the power x by n and gnx is equal to x to the power n. So that f comma g both converge pointwise on 0, 1. So limit n tending to infinity Fnx is equal to limit n tending to infinity e to the power x by n is equal to e to the power 0 is equal to 1. For x belongs to close 0, thus Fnx converges pointwise to Fx is equal to, meaning thereby Fn, if Fn is a mapping from A to R and F is the mapping from A to R. So that f comma g both converge pointwise on close 0, 1. Limit n tending to infinity Fnx, limit n tending to infinity 0, 1. For each x belongs to close 0. For each x belongs to close 0, 1. So Fnx converges to pointwise to Fx is equal to 1. So this is a pointwise convergence. Okay. Now we solve the second example. If 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 g and x is equal to x to the power n, by taking limit n tending to infinity g and x is equal to limit n tending to infinity x to the power n. So this is limit n tending to infinity x to the power n 1, 1 if x belongs to close 0. Okay. If x belongs to close 0, 1, meaning thereby, okay, close 0, and limit n tending to infinity 1 to the power n is equal to 1 if x is equal. Okay. If limit n tending to infinity, if it is 0, then it is 0. If it is less than to 1, then it is 0. So this is a, thus thus g and x converges pointwise to gx when 1 if x is equal to 1 and 0 if x belongs to close 0. This is a point wise function. इसको क्या कहेंगे? Point wise. So how we find the point wise function? In this question, it is said that if x is equal to 0, then it is 0. If x is equal to 1, then less than 2, then it is limited tending to infinity. So how we will find the point wise convergence? So first of all, we see the domain of the convergence. The domain of the convergence. First of all, we concentrate on this part. If x belongs to close 0, 1, then what is the limit at infinity? If x belongs to that interval close 0, 1, then what is the limit at infinity? So this is the pointwise convergence. This is the pointwise convergence. Now, if we discuss next example such that Suppose that fn such that 0 comma 1 to r is defined fnx is equal to n upon nx plus 1. Then since x does not equal to 0, so limit n tending to infinity fnx. This is 0 comma 1 because x does not equal to 0. We see this domain 0 comma 1. So fnx is equal to limit n tending to infinity 1 upon x plus 1 by n. So this is 1 by so so fn tending to f pointwise where f such that 0 comma 1 to r is given by fx is equal to 1 by fx is equal to 1 by. So we have mod of fnx is less than 2 because this is a bounded function for all x belongs to 0 1. So each fn is bounded on 0 comma. You see this function is bounded on 0 comma 1 because if we put 0 because the interval does not contain 0 1. So the interval contains the values between 0 1, and if we put the values between 0 to 1 for x, then it is a bounded function and it is less than to some quantity. So mod of fnx is less than to n for all. So fn is bounded on 0 comma 1. But 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 their pointwise limit f is not. ओके क्योंकि इसकी पॉइंट वाइज लिमिट क्या है बाउंडेड नहीं बट देयर पॉइंट वाइज लिमिट f is not bounded. Okay, thus because the graph of this function f of x is this, okay, 1 by x, इसका ग्राफ इस तरीके से बनेगा. So this is not a bounded in 0 1. So thus pointwise convergence does not in general preserve boundedness. Preserve preserve boundedness. Okay. So from this example, we see that the given function is bounded, but their pointwise limit is not bounded. So preservance, so the pointwise convergence does not preserve the boundedness property. Now we see the next very important example. Suppose that fn such that 0 comma 1 to R is defined by is defined fn x is equal to x to the power x. If x lies between 0 to 1, then xn tending to 0 as n tending to high. If x is equal to 1, then xn tending to 1 as n tending to 1. So fn tending to f pointwise, where where so question is that suppose that fn from 0 close interval 0 to 1 to r is defined by fn x is equal to x to the power n. Okay. If x lies between 0 to 1, then xn tending to 0 as n tending to infinity. While if x is equal to 1, then xn is equal to 1 as n. So fn tending to a pointwise, where fx is equal to 0 if x lies between 0 to 1 and 1 if x is equal to. Although each fn is continuous, each fn is continuous on closed 0. Each fn is continuous on closed 0. Why? Because fn is a polynomial function. Fnx is a polynomial function of closed 0. So it is a continuous on closed 0, 1. Their pointwise limit, their pointwise limit f is not. F is not because this function is not continuous at 0. If we find the limit of fx at 1, then f of 1 minus h कितना हो जाएगा 0 and f of 1 plus h is 1 and f of 1 is okay. So function is not continuous at 1. Function is not continuous at 1. So their pointwise limit f is not ब्रैकेट में लिखना है it is discontinuous at. It is discontinuous at discontinuous at. We see from this limit n tending to infinity 1 minus h is 0 because less than to 1. If 1 plus h, then it is 1. If it is 1, then it is okay. Thus pointwise convergence does not in general preserve continuity. Continui continuity. Okay. So from this example, we prove that the pointwise convergence does not preserve continuity. From previous example, we saw that the pointwise convergence does not preserve the boundaries. So from these two examples, we have very important result that the pointwise convergence does not preserve boundedness as well as the so right. The general result is that the pointwise convergence The pointwise convergence does not preserve the boundedness and continuity and continuity. Okay, so this is a very important result. Now we saw the next question. The question is that define fn such that close 0 1 to r by fnx. So fnx is nothing but 2n square x if x lies between 0 to 1 by 2n. 2n square 1 by n minus x if 1 by 2n is less than 2x is less than to 1 by n and 0 less than or equal to. Okay, now we solve this problem. If x lies between 0 to 1, then fnx is equal to 0 for all n greater than or equal to 1 by x. If x lies between 0 to 1, how this is possible? So if x lies between 0 to 1, then where the function lies? So if x lies between 0 to 1, if limit n tending to infinity, so 0 to 1, 0 to 1, meaning thereby this 0 to 1. Okay, लिमिट एन टेंडिंग टू इन्फिनिटी पे ये जीरो की तरफ टेंड हो जाएगा. ठीक है, ये लिमिट एन टेंडिंग टू इन्फिनिटी करेंगे तो 0 x लाइज बिटवीन 0 to 1 एंड द वैल्यू ऑफ fx इज 0. fnx is 0 for all n is greater than or equal to. So fnx tending to 0 as n tending to infinity, and if x is equal to 0, then if x is equal to 0, then fnx is equal to 0. X is equal to 0, then fnx is equal to 0 for all n. So fnx tending to 0 also. It follows that fn tending to 0 pointwise on close 0 1. This is the case even though maximum of fn is equal to n tending to infinity as n tending to infinity. Thus, a pointwise convergent sequence of functions, a pointwise convergent sequence of function need not be bounded, even though, even if it, even if it converges to C, even if it converges to 0. So, in this scenario, we see that what is the problem? The problem here arises that close 0, 1. If it is x, if you take the value of closed interval x is 0, then we get the value is 0. If it is 1, then it is goes to infinity. So if x lies between 0 to 1, if x value of x is 0, then it is 0, and if it is 1, then it is also 0. So for all n is greater than or equal to 1 by x. If we put the place of n is equal to 1 by x, or in the place of x is equal to 1 by n, then in this criteria is it is soluble. And fn tending to 0 as n tending to infinity. And if x is equal to 0, then fnx is equal to 0. So fnx tending to 0. And also we see that if n tending to infinity, and if you take x is equal to 1, then this goes to infinity. Then this goes to this function 2n square x is this. If we take fnx, if we take fnx is equal to 2n square x, and if x is equal to 1, then limit n tending to infinity fnx is tending to infinity. So here it is so that it follows that fn tending to 0 pointwise on 0. This is the case even though maximum of fn tending to infinity. Maximum of fn tending to, okay. So limit convergence, pointwise convergence exists, but the given function is not a bounded function. Given function is not a bounded. So these are the very important results. Okay. These are the very important result: boundedness, convergence, continuity. Okay. Now we see the next very important question. The question is that define Fn such that R to R by Fnx is sin nx upon then Fn tending to 0 pointwise the sequence Fn dash x is cos of nx. Fn dash x cos of nx does not converge pointwise on capital R. For example, Fn dash pi is minus does not converge as n tending to. Thus, in general, thus in for example, f(n) dash pi is equal to minus 1 to the power n does not converge as n tending to infinity. Thus, in general, thus in general, one cannot differentiate a pointwise convergent sequence. This is because the derivative of a small may be large. Okay, so from this question, we analyze that if a function converges pointwise, but their derivative does not converges pointwise. Because if limit n tending to infinity, if we take this limit n tending to infinity sine nx upon n, then this goes to 0. This goes to 0. So it is converges pointwise. But this fn dash x is cos nx. Okay. This is cos nx does not converge pointwise on R. Okay. For example, if fn dash pi, then this is minus 1 to the power n does not converge because this oscillates minus 1, 1, minus 1, 1 oscillates finitely. So this is does not converge. It does not approach to 0 as an tending to. Thus, in general, one cannot differentiate a pointwise convergent sequence. Cannot differentiate a pointwise convergent sequence. This is because the derivative of a small rapidly oscillating function may be large. So from this result, we analyze that if a function converges pointwise, then their derivative does not converge pointwise. It is not necessarily that it is converges pointwise. So from above example, we see three very important results, four very important results, that if it a function is a continuous, is a sequence of a function continuous, then their pointwise limit does not a continuous function. If sequence of the function is a bounded function, then their pointwise limit does not a bounded function. If a function converges to 0, then it is not necessary that it is bounded function. Fourth result is that if a function is a converges to a pointwise convergent, then it is not necessarily that their derivative is converges pointwise. So there are four results, and we prove from there from the some counter examples. So these counter examples are very useful for your upcoming competitive exams such as IIT exam, NET JRF, CSIR, NET JRF, because many of the questions, many of the options of the questions will be distracted, will be uh, dominated by using these examples. Okay, so you learn these very important examples, that which one of the example is used for which of the option. Because if there is a statement that if the pointwise limit of the derivative of the function is convergent or not, then you give the counter example of that and you cut out that options from the questions. So you always learn the counter examples of the some important chapters. Okay, so you make a list of the counter examples. So this is a very useful for your upcoming examination as well as your semester examinations. Okay, now we say The next very important example questions is that, so the question is that define fn such that r to r by fnx is equal to x square plus 1 by, if x does not equal to 0, then limit n tending to infinity x square plus 1 by n. So this is x square upon mod of x. So this is mod of x. Okay. So define fn such that r to r fnx is equal to x square upon x square plus 1 by n. So this is a function. If you take the limit n tending to infinity, then this is a modulus function, mod of x. While while fn 0 is equal to 0 for all n belongs to capital. So fn tending to mod of x pointwise on the limit mod of x not differentiable, at 0, even though THOUG though all of the fn are differentiable on capital. Okay. Now we see this is modulus function x when x is greater than or greater than 0, and minus x when x is less than 0, at 0 when x is equal to 0. Okay. So this is a modulus function, and the graph of this function is this mod of it. So this is the corner points. So at the corner points, the function is not differentiable. So from this we analyze that fnx tending to mod of xx pointwise. Okay. And the function is also the limit mod of x is not differentiable at 0. So from this we also see that the function is continuous and differentiable. This is the function is continuous and differentiable, but their pointwise limit is not a differentiable function. Okay. So this is the counter example for, this is a very important example for you. Now we saw very important example question is that, very important question is that define fn such that r to r by fnx is equal to 1 plus x by n. Then by the limit formula for the exponential function, which we do not prove here. So fn tending to the power x pointwise on r. So by the limit formula, then by the limit formula for the exponential, which we do not prove here, fnx tending to e to the power x pointwise on So this is the basically the most important examples of the point-wise convergence. Point-wise convergence. Now we also see again what is the uniform convergence. Again we see what is the uniform convergence. Suppose that Fn is a sequence. Fn is a sequence of functions Fn such that A to R and F such that A to R, then Fn tending to F uniformly. If for every epsilon positive there exists n belongs to capital N such that n greater than to capital N implies that mod of Fnx minus Fx for all x belongs to. So what is the uniform convergence? So uniform convergence suppose that Fn is a sequence of functions Fn such that A to R and F such that A to R. Then Fn tending to F uniformly on A if for every epsilon positive there exists n belongs to capital N such that n if n is greater than 2 capital N implies that mod of Fnx minus Fx is less than 2 epsilon for all x belongs to. Now question is that the sequence Fnx is equal to xn. We say that converges pointwise. Converges pointwise because we already proved in above slides that it is converges pointwise on close 0 1, but not uniformly on close 0 for x lies between 0 to 1 and epsilon lies between 0 to 1. We have this is mod of Fnx minus Fx is equal to mod of xn is less than 2. Because if x lies between 0 to 1, then what is the value of Fx? You see, Fnx is equal to x to the power n, then Fx is equal to 0 when x lies between 0 to 1 and 1 and x is equal to 1. So here we take this domain. So here Fx is equal to 0. So this is mod of xn is less than 2 epsilon. So if and only if x lies between epsilon 1 by n, since epsilon 1 by n is 1 for all n belongs to capital N. No capital N works for all sufficiently. close to 1. Although there is no difficulty at executing. The sequence does, however, converge uniformly on close 0 for every 4 we can take below. So if mod of xn is less than 2 epsilon, see this. If mod of xn is less than 2 epsilon, then xn is less than 2 epsilon, then ln x. This is n. If you apply this xn is ln e, n is ln epsilon upon ln x. If so, this small n is less than 2. Okay. So this does not fulfill the criteria that this does not satisfy this does not satisfy that small n is greater than to capital N implies that mod of fnx minus fx is less than 2 epsilon for on x cubed. So this function does not satisfy the criteria of the uniform convergence. That is why this function is not uniform convergence. Now we saw the next very important example. The function fnx is equal to sine nx upon n converges uniformly to 0 on capital R since mod of fnx is equal to mod of sine nx upon n is less than or equal to 1. So mod of fnx minus 0 to epsilon for all x belongs to capital if n is less than 2. If n is less than 2, because mod of fnx is less than or equal to 1 by n. So 1 by n is less than 2 epsilon. So n is greater than 2 1 by epsilon. So this satisfies the criteria that n is greater than capital M, implies mod of fnx. Okay, so this function satisfies the criteria. That is why this is uniform convergence. Now we again see a very important criteria, that is Cauchy condition of uniform convergence. Cauchy condition for uniform convergence. The definition is that a sequence fn of functions fn such that a to r is uniformly Cauchy on capital A if for every epsilon positive there exists capital N belongs to capital N such that m comma n be two numbers always greater than n implies mod of fmx minus fnx for all x belongs to capital. So a sequence fn of functions fn such that a to r is uniformly Cauchy on A if for every epsilon positive there exists n belongs to capital N such that m comma n greater than 2n implies that mod of fmx minus fnx is less than 2 epsilon for all x belongs to. So this condition is very important. For Cauchy, this condition is very important, and for uniform convergent, this condition. Important problems, we see the important problems that now we see very important concept here is that properties of properties of uniform convergence. So boundedness. So first we consider suppose that fn such that a to r is bounded for every n belongs to capital and Fn tending to F uniformly on capital, then F such that A to R is bounded on is bounded on. So suppose that Fn such that A to R is bounded on capital A for every n belongs to capital N, and Fn tending to F uniformly on capital A, then F says that A to R is bounded on capital. Then F says that A to R is bounded on capital. Question is that Fnx is equal to n upon nx plus, so fx is 1 by x. X is 1 by x belongs to. Now, mod of Fnx minus fx, mod of n upon nx plus 1 by 1 upon x nx plus 1 ns. Thus, given if some positive, choose n is equal to 1 by a square and then mod of Fnx minus fx for all x belongs to. If n is greater than or equal to n is greater than, which proves so the limit function f is bounded on a1. So this limit function is, so this limit function is bounded on. So next property, we also discussed the next property, continuity. So uniform convergence preserves the property of continuity. Preserves the property of, meaning thereby continuity of the uniform limit So if Fn is continuous, then their uniform convergence is also. So I hope that this is a very important concept for all of you, and differentiability. And then one important concept is that the uniform convergence of differentiable function does not imply anything about the convergence of their derivative or the differentiability of their differentiability. So I hope today's lecture is very beneficial to all of you present here, and I hope and you see this lecture at my YouTube channel. Okay. In the next lecture, I think I will discuss about the Lebesgue method theory and its properties. So thank you very much for listening me carefully. Thank you to all of you present here. I stop this lecture from here. एक टेलीग्राम ग्रुप है अंक मैथ्स फोरम के नाम से, टेलीग्राम ग्रुप. सो ऑल ऑफ यू, मैं अंक मैथ्स फोरम, ठीक, ये टेलीग्राम ग्रुप है. तो आप लोग इसको ज्वाइन कर लीजिए और वहां पे आप डिस्कस कर सकते हैं कुछ भी क्वेश्चंस को, उस क्वेश्चंस की प्रैक्टिस करने के लिए. अंक मैथ्स फोरम, दिस इज अ टेलीग्राम ग्रुप. ओके, अंक मैथ्स फोरम. So this is also in my YouTube channel name and this is also my Telegram channel name. Okay. So all of you join here and you will discuss. Sir name क्या है? Ank Maths Forum. This is a Telegram group. Okay. Telegram group है and we will join this. So thank you. Telegram link. Uh, I I will share it in the next lecture. Okay. Okay. Thank you very much. तो ऑल ऑफ यू ज्वाइन माय यूट्यूब चैनल एंड सी दिस लेक्चर. अंक मैथ्स फोरम के नाम से है लेक्चर. ओके, so you will see here.